껴져 있는 걸로 하면 돼요.
그럼 새거 있어. 어? 아 여기 있네. 이거는 종이 한 개. 색연필 가져가서 주세요.
이게 이름이
안 만들었어요?
저번에 만들었던
여기서 한번 찾아볼래? 여기랑 섞지는 말고. 없어요?
저도
잠깐만. 여기서 한번 찾아볼래? 한번 찾아볼래? 네. Okay, let's start from where we stopped. So I'm going to explain Dodge-Josa algorithm again, and I'm going to walk through in detail. So the Dodge-Josa problem is to find the function, find whether the function is balanced or constant. So function is called balanced if it has the same number of outputs, 0 or 1. It's constant if it has all the same output, 0 or 1. So I'm not considering all kinds of function. I only take a consideration of two kinds of function here. So having this assumption, how do I find out whether my function is balanced or constant is the problem. So when you use the classical algorithm, you need to ask function or ask to the query the function at least 2 to the n minus 1 times plus 1 in order to find out what that is for the worst case scenario. But when you use the quantum circuit and quantum algorithm, you can find whether it's balanced or constant by single query. So here is the circuit. First, you put the Hadamard gate on every single input and output register, and then apply Oracle, and then apply Hadamard on the input register again, and measure every input register. Okay, so that's simple and almost same as Dodge-Josa, only differ by the number of input. And let's compute step by step. So we separated each step into 4, starting from 0. So at the 0 step, it's obviously 0 and 0 tensor, right here, and 1, sorry. The output register is initialized as 1. And once you apply Hadamard gate, the input register becomes the superposition of all the possible states. That's actually what is good about having Hadamard and using quantum states for the computation, because by applying n number of gates, you can get 2 to the power of n number of states. And then you get the negative cat for in output register. So there are some typos on the coefficient side, so keep that in mind. And let's apply the oracle. So oracle says, depending on the value of x, you get the value of the output states are changed. So here is one possible choice. Okay, so because of the tensor product with these two, depending on x, here it has to be bold-faced x, you get the value f of x, either 0 or 1, but when you add to 0, it's always the same. And because of these tensor product, you get this part. Okay, and you can see that f of x and 1 plus f of x are always the pair of 0 and 1. Only difference is that depending on whether f of x is 0 or 1, you change the sign. So that part goes here, and the general form is this, 0 minus 1. So f of x equals to 1 means that cat 1 minus cat 0, so you get minus 1 applied to 0 minus 1. And f of x equals to 0 means that 0 minus 1 with positive sign. So that's right after applying the oracle. Now you have to take the Hadamard gate back again. We're not going to compute again because it's going to be complicated. But let's think about, let's assume that we already done that. And then let's make it a little bit simpler. So what we're going to do is assuming that the function is constant. So that case, then these sign is all positive or all negative. Doesn't matter what x is. So I can take out side of the summation. So in that case, becomes a plus or minus here. And it's simply an Hadamard gate applied to, so this is the same Hadamard gate here, to these superposed state. But how do we get this superposed state anyway? It's given by applying the Hadamard gate on every single input register when it's initialized at 0. So what we are doing here is we applied Hadamard gate twice for each input register. So the final result is plus minus 2 this. So that means if f is constant, then you will always measure 0 on the input register. Okay, so let's change the cause. So if you observe all the zeros as a measurement outcome in input register, then it means that the function is constant, unless there is any possibility of having 0 cat when f is not constant. So let's take another case. The opposite case is when f is not constant. That means if it's balanced. So if f is balanced, then we have the same number of zeros and ones as an output, right? So think about this computation after, actually maybe way here. So well, maybe before here, right here, here. So we have same number of zeros and same number of ones. Doesn't matter at which x we get 0 or 1, just get 1 or 0, right? So I want to think about is there any possibility to have 0, 0, 0, 0 once you apply the Hadamard gate back to the again at the third stage. So I'll give you an example. Let me give an example here, concrete one, by writing down this. So let's think about the case when f is balanced. How many? So let's take the n equals to 2. I have x as 0, 0, 0, 1, 1, 0, 0, 0, and f of x to be 0, 1, 0, 1. Okay. Now let's think about from beginning. Psi 0 is 0, 2, 1. So that's an input, and that's output register. And psi 1 is So I'm going to forget about the coefficient, not gonna too much strict about the coefficient. So it's 0, 1, 1, 0, plus 1, 1 times 0 minus 1. So that's after applying all the Hadamard on input and output. Let's try to take the oracle. So the oracle says, depending on the value, I change the output register. So 0, 0 becomes 0 because we have 0 value here. And 0, 1 is, oh, sorry, so forget about this. So 0, 1. And then 0, 1 has a value 1, right? So now it's 1 minus 0. And then 1, 0 has value, function has value 0. So we have 0 minus 1. Look at this, remember this table. I just gave you an example of balanced function. And then the last one is 1, 1. So 1 minus 0. Okay. So I'm going to take the Hadamard back again. So let's see what happens. Here, okay, we have, let's make it clever. So, well, in principle, what would happen when I take the Hadamard gate on the input register is 0, 0 becomes plus plus, 0 minus 1, and so on. So it's minus minus at the end. So you're going to, I mean, you could expand all the terms into zeros and ones and then see if there is any cat state of zeros only. But let's be a little bit clever. So I want to see, I only interested in whether if I expand, what's going to be the part that is tensor product to 0, 0 cat on input register. So I don't care about the others. So what is this? What is this part? So how do I get this part? So one way I can get this is taking 0, 0 from here, right? So I have, in that case, I have these as my counterpart for the tensor product. And let's do the same thing for here. So when I take the Hadamard gate on here, it becomes plus and minus and blah, blah here. But then I have to take 0, 0 again here. But now, when I take 0 cat from plus cat or minus cat, they both have plus sign. So it doesn't matter whether it's plus cat or minus cat. I can just take 0, 0 out without considering any sign here. But now we have this, right? So, so first this goes here, and also this goes here as a sum. And we can do the same thing for here and here, right? All this goes into the sum and sum them up to something that is going to tensor product with 0, 0, okay? So how did we get this? How did we get this part? So this part is because you get f of 0, 0 equals to 0. So we get minus 1 to the 0 is 1. So we get the positive sign. But here we switch the sign because we have f0, 1 equals to 1, and 1 minus 1 to the power of 1 is minus 1. We switch the sign. Okay? So if you have a function which is balanced, then you will see the equal number of sign plus and equal number of to the equal number of sign minus. Okay, so you will see the same number of these, like this one, to the same number of these, as you can see right here in this specific example. So you have 2 plus cats, 2 minus cats, right? If you I mean, not minus cap, sorry, it's not minus cap, minus plus cap, sorry. So you have 2 plus cap and 2 minus a plus cap. So let me write it again. So this is plus plus and minus plus minus plus, okay? So if you add those together, they vanish, right? They disappear. So this all becomes 0. Okay? So you can think about this in a general situation. So you had minus 1, a sum over x from 0 to 2 to the n minus 1. We had a sum of minus 1 to the power of f of x, x times, let's say, it's a minus here. I just take the minus here. So when I take the Hadamard on here, on all of these here, on this input register on here, so actually Hadamard goes here, then if I'm only considering the 0, so this is n qubit state, 0 qubit state for the input register, then what I get is here x range from 0 to 2 to the n minus 1 to the power of fx times minus. Okay, so it's something more is appended here, but I don't care. I only want to see what is there going to be a 0 n qubit state in my outcome. But it turns out that if f is balanced, then this whole thing becomes 0. So this whole thing becomes 0 vector, 0 quantum vector, quantum state. So therefore, it doesn't exist. So that doesn't exist. Okay? So I don't have to worry about, even if I see all the zeros after measurement of the input register, there might be a chance that f is not a constant. So if I see all the zeros on the measurement outcome, then it must be a constant. Otherwise, there should be some 1 in the measurement outcome of the input register because of this computation. Okay? So from the single query of an oracle, I can determine whether function is balanced or constant. So before we move on to the next one is more interesting. Is there any question? Do you have a question? No? You forgot the name tag. So can you take the name tag? Yes. State, yes. Mm-hmm. So there's no way you can check what the coefficient is.
We just check the 0 is exists or doesn't exist.
Yes, basically that's it. So there are only 2 cases. Either the state of the input register has a state as 0 base state or none.
Then it means that it is balanced or
So when it's all 0, it's constant. When there's no 0, it's balanced. So any other question? Yes.
저 n 큐빗에 0이 이제 존재하지 않는 게 저기 앞에 붙어 있는 게 0이 되는 건데 저걸 이해를 못했습니다.
Oh, why is this becomes 0? Why is this becomes 0? So in this example, you can okay, so maybe I can give you more detail. So I omit two steps. I omit two terms here. Let me make a space here. Okay. So I'm going to write more. Okay, so then here, let me erase this. Okay, so here I have plus minus 1 minus 0. So I'm looking at this one, okay? And I have minus plus 0, 1. Okay, so I have four, it's not four, but there are four sums. I want to check what's the coefficient of the quantum state when the input register is at the base state 0. Okay, that's my concern. I don't care about the other state. So I collect them by taking, so if you look at this one, so this one is simply plus tensor plus, so it's 0 plus 1 tensor 0 plus 1. Okay, so if I want this out of here, then I can take this one in my distribution law. Okay, so if I take this multiplying or tensor product, then I get this. Okay, so what's the tensor product? What's in the output register? It's this. Okay, so let me write this explicitly. So I have basically it's minus, so I will say it's minus here. So actually okay, so there's a typo, so it's not plus, I'm sorry. So this is all minus, by the way. So let me erase this for now. And so this is minus, and how about here? So how about here? I also want the 0, 0 only. So this one is plus tensor minus, which is 0 plus 1 tensor 0 minus 1. So I'm only looking at this one. And in order to get 0, 0, I need to take these two tensor product. Okay, that's how I get this part. Okay, then what is it multiplied to? What is it tensor product to? This one, right? So this is minus cat. Okay, so I'm going to add minus cat because of the second term. So I'll do the third and fourth. So on the third term, I get 0, 0. Again, the sign is positive in this side, but then I get the minus cat here. Then same thing for here, sign is still plus, but I get minus cat because of this. So I get canceling each other. So I get 0. So it's not all of it. Sorry. So it's not all of it. I have other terms, but I don't care. I just want to see whether there is a chance to observe 0, 0. But there's no chance to observe that because this is 0. So whatever the state is, it doesn't have the possibility of measuring 0, 0 on the input register. Okay? Because it's all vanished. Well, here, this one.
하다 보면 데이트 들어가고 그럼 하나하나 다 보여주시는 거죠.
네. 네. 다 한 게 아니죠, 지금. 다 하지 않고 영영만 했잖아요. 영영. 그렇죠. 네. 관건은 영영이 나오냐 안 나오냐고요. 아니 컨스턴트가 이면 함수가 컨스턴트면 0만 나오고 컨스턴트가 아니라 밸런스드면 0이 안 나온다는 거예요. 아니 밸런스드다라는 게 아니고 지금 밸런스드라고 가정을 했잖아요. 밸런스드 그러니까 이게 밸런스잖아요. 밸런스드 예제인데 밸런스드면 항상 이렇게 된다. 건 뒤에서 보였고 밸런스드면 0이 안 나온다고요. 자, 컨스턴트면은 0만 나오고 밸런스드면 0이 안 나와요. 그러면 이제 반대로 인과관계를 바꿔서 내가 0을 봤으면 무조건 컨스턴트겠죠. 0이 안 나오고 하나라도 1이 보이면은 밸런스드겠죠. 그렇게 이제 보는 거예요. 그렇게 나오도록 디자인을 한 거죠, 사실은. UF는 F2. 여기 F1에서 F2로 갈 때 UF가 적용이 됐죠. 여기 보시면은 지금 제로니까 인풋이 제로니까 이 F00는 0이라고 가정했잖아요, 여기서. 그러니까 부호가 안 바뀌고 그냥 1로 들어간 거고 여기는 x가 0, 1이잖아요. 사실 거꾸로 읽어야 되는데 그냥 0, 1이잖아요. 그럼 이제 함수값이 0, 1이라고 가정을 했으니까 마이너스 붙여서 들어간 거고. 네. 표의 00 이런 순서대로. 네. 아, 여기가 참, 못하겠군요. 네. 맞습니다. Any question? Yes. Yes.
그것도 혹시 다음에 해주시면
We already did it. So in here, so if it's constant, then this is constant, right? So it goes out as a plus or minus, go outside of the sum. So what we're doing here at the final stage, when we apply the Hadamard twice, the second time, then we are applying Hadamard on these proposed state. Okay, that's only because we assume that the function is constant. If it's not constant, I cannot take out this sign outside of the sum, right? So then think about how we got this. This is after we apply Hadamard on zero-base case, zero-base state, right? So we're applying Hadamard on each register twice. So this is identity gate. So we get 0. Okay, so anyone else? Yes.
혹시 마지막 순서로 값에서 y가 y의 펜만큼 혹시 결과가
Y의 뭐라고요? 펫만큼?
y 캣이 y 캣 플러스 fx y 플러스 fx 캣이
네.
그러면 함수의 결과값을 도출해야 되잖아요. 그 저희 계산을 해낸 값의 뒷부분을 보면서 그 뒷부분에서 처음에 있던 y를 불리언을 계산으로 빼줘야 돼요.
무슨 말인지 모르겠는데. 지금 So look at, maybe I should go here. So this is the oracle, okay? So if y is 0, then this becomes simply f of x. If it's 1, it becomes 1 plus f of x. Okay? So if it depends on what x and what value of f of x is, it could be 0 and 1, or it could be 1 and 0, right? Right, so when y is 1, then it's a bit flip. But the thing is, no matter what value of your function f of x is, what value for f of x is, if you take the sum of these two, let's say if you take the sum of these two, then you get always plus ket, right? So 0 plus 1 is plus ket, right? And 1 plus 0 is also plus ket. So that's why we first initialized it to be minus ket, because you cannot tell the difference in this case. In this case, you don't have difference. If it's a plus, then you don't have a difference. But if it's a minus, now you get different state. So this one is not minus ket, and this was minus ket. Now you can tell the difference, right?
플러스일 때는 서로의 디퍼런스를 구분할 수 있다고 하셨는데
Mm-hmm. So if it's a plus, then they are both 0 plus 1. Okay.
결과를
So this is when f of x equals to 0. And this is when f of x equals to 1. Right?
관계는 인첩이 아니라 얽힌
So it's simply an input state. Okay? This is an output state. There's no relation. Just an input state and what? Input register and what output register. After you pass it to Oracle, you change the output state. This is for X. Sorry, this is for Y. Sorry, this is for Y. So if you, so I don't want to get too confused, but let me say again, this diagram is only makes sense when X and Y are either 0 or 1. You cannot plug in this Y, the plus ket. It doesn't make sense. But I'm assuming that we are taking the 2-qubit state or 3-qubit state altogether. But if you just look at this diagram, it seems like you have a tensor product unentangled state of input and output register. That only applies when you have Y either this or this one, not a superposed state. Okay, so you have to look at this diagram. You have to understand the diagram only in this way, like this one. This is.
아까 말씀하신 빼기 상태에 언급하신 거 그냥 다이어그램에서 벗어나는 거 그냥 한번 보여주신 거 같아요.
So when you apply this diagram, this is not the. This is just an example. When you apply the oracle, you're going to apply the oracle on this multi-qubit state, assuming that this multi-qubit state are somehow on this whole state is acting as one qubit state. Okay, so this whole thing gives you the quantum state as an n qubit state, n plus 1 qubit state. You're applying the oracle on these n plus 1 qubit state, not individually. Okay? So therefore, if I take the one big input register, you can consider whatever the superposed state that you have, or also for the output register, you can take whatever the superposed state inside here. but you cannot take separately this input state and output state, and then whatever you got here is the tensor product of these two, because this diagram only applies to when x and y are either 0 or 1, but in real case it's not. Okay, so what's actually happened is what we just calculated here. Okay, so we're not looking at case by case. We're not looking at when 0, 0, 0, 0 is here, the output is that, and whatever that input is here, output is that. We're not looking at case by case. We're taking entire quantum state and then put it into the oracle and see what happens. So, is there any other questions? Yes.
다른 질문이긴 한데 밸런스를 정리해서 확인의 팁
Okay. Yes. Okay, so I should go back to here. So what I mean by the cardinality is the number of minus and plus in the sum. So how many 1 in this sum if f is balanced? Two to the n minus 1. And how many minus 1 in this sum? So there are total 2 to the n terms in this sum. Each term is either 1 or minus 1. So 1 and minus 1 is depend on the value of function. So we assume that the value of function is either 0 or 1, and there are same number of values as an output. So there are equal number of 1 and minus 1. Okay? So we have 2 to the n minus 1 plus 2 to the n minus 1 minus. So they are all cancelled out to 0. That's what I'm explaining in the slide. Okay? Does you make sense? Okay? Surname. 인규? 이인규? Does it make sense? Okay? Yes. No. 그 비트일 때만 작동하는 게 아니고 이 다이어그램은 비트일 때를 설명한다는 거예요. 지금 이 다이어그램이 어떻게 보면은 지금 그런 게 아닌데도 이 x랑 y의 그러니까 그냥 분리돼 있으니까 x랑 y의 텐서 프로덕트인 것처럼 보이잖아요. 거쳐가면 또 이거랑 이거의 텐서 프로덕트인 것처럼 보이잖아요. 이런 모양, 이런 거는 이 x랑 y가 0 아니면 1인 비트일 때만 가능한 거예요. 그때만 그렇게 되는 거고, 실제로는 여기에 이런 베이스 스테이트 하나가 들어가는 게 아니고 인탱글이든 뭐든 이게 슈퍼포즈 스테이트로 들어갈 거 아니에요. 그래서 이런 식으로 텐서 프로덕트 나오는 건 아니라고. 네.
게이트에 넣어가지고 서로 간에 그거를 분리할 수 없는 상태로 나오는 그게 어떤 의미가 함수
그러니까 이게 중요한 게요. 그 퀀텀 스테이트에서는 퀀텀 서킷에서 클래시컬 이제 알고리즘으로 지수승만큼 걸리는 어떤 연산을 한 번에 끝날 수 있는 거잖아요. 할 수 있는 이유가 우리가 이렇게 하다마드로 다 중첩을 시켜놓고 한꺼번에 넣었으니까 되는 거거든요. 중첩 안 시키고 그냥 000 넣어가지고 그냥 아웃풋을 봤어요. 이게 나왔네? 할 수 있죠. 그러면은 클래시컬 하는 거랑 똑같은 거잖아요.
그게 아니라 다이어그램을 표현할 수 없는 상태가 돼야지 양자 컴퓨터로 쓸 수 있는
그러니까 다이어그램으로 표현할 수는 있죠. 이렇게 표현은 되는데 이제 이 상태를 보세요. 그러니까 지금 헷갈리면 안 된다고. 0이랑 0이랑 1이랑 텐서프 돼 있는 거잖아요. 얘들은. 근데 이제 하다마다 거치고 얘가 되는 순간 더 이상 0 이것만 그냥 따로 떼서 보면 안 된다고요. 0 하다마드에서 뭐 이거는 아무것도 안 바뀌니까 그냥 하다마드 된 플러스 상태로 있겠. 그러니까 하다마드 두 번 했으니까 0 상태로 있겠지. 얘도 막 0 상태로 있겠지. 얘는 뭐 y 플러스 x 되겠지. 얘들 텐서 된 거겠지. 그렇게 보면 안 된다고요. 그렇게 해석하면 안 된다고. 다이어그램 자체는. 다이어그램을 우리가 계산한다고 하는데 얘를 따로따로 계산하는 게 아니고 이 전체를 n 큐빅 스테이트로 보고 스텝마다 이 스테이트가 어떻게 표현되는지를 계산을 해야 돼요.
처음 시작. 1 넣었을 때는
네. 근데 표시를 해야 되니까. 어디가 인풋이고 어디가 아웃풋인지는 표시를 해야 되니까. 예.
그 결과가 인풋 아웃풋 고백할 수
아니 알 수 있죠. 사실 그러니까 우리가 그 퀀텀 컴퓨터에 그러니까 이게 약간 이제 물리적으로 어떻게 되는지 설명을 하면은 큐빗이 있어요. 큐빗마다 이제 그 값을 읽을 수 있는 장치가 있단 말이에요. 그러니까 내가 뭐 양자 컴퓨터에 이제 100개의 큐빗이 있는 양자 컴퓨터라고 하면은 내가 100개 큐빗을 각각 매저를 할 수 있어요. 그러니까 내가 어떤 큐빗을 인풋으로 하고 어떤 큐빗을 아웃풋을 할지 어사인을 할 수 있다고요. 그리고 내가 나중에 이런 서킷을 지나가지고 내가 인풋 레지스터를 0번부터 10번까지 했으니까 여기서 0번부터 10번 큐빗을 읽어야겠다. 그럼 그 인풋 큐빗을 내가 읽는 거예요. 알 수 있죠, 내가. 어떤 큐빗을 어떻게 사용했는지는 알 수 있죠.
해야지.
유용한지? 이게 자체가 유용한 거죠. 이 문제를 획기적으로 빨리 풀 수 있는 방법이잖아요. 지수번만큼 내가 시행을 해야 되는 거를 한 번의 시행으로 끝내잖아요. 그게 유용한 거죠. 네.
하단할 게이트를 굳이 왜 붙여야 되는지가 이해가
없으면은 어떻게 되겠어요? 0000만 들어가면은 그 함수값 하나가 나올 거죠.
하단화 이 n 승계를 다 그냥 집어넣어가지고 확인을 할 수가 있는 것인가?
뭐 이론적으로는 그렇죠. 한꺼번에 볼 수 있으니까. 예. 하나마다 안 고치면은 그냥 F0000이 무슨 값인지 뭐 알 수 있죠. 네, 알 수 있죠. 오라클 거치면은. 그러니까 여기다가 이제 뭐 0 넣고 이거 다 없애고 거치면은 여기에는 F000 값이 바뀌어서 나올 거 아니에요? 그러면은 그거 읽어서 이제 오류가 없다, 그러니까 메저먼트 에러가 없으면은 그 값이 이제 함수 값이 되겠죠. 근데 우리가 원하는 거는 밸런스드인지 컨스턴트인지를 알아내는 건데 그런 식으로 하면은 클래시컬 한 거랑 똑같잖아요. 지수번만큼 이 회로를 돌려야 된다고. 근데 이렇게 하면 한 번에 되니까.
우리가 생각하는 원래 생각봤던 일반적으로 샌드와 노게이트가 합쳐진 거예요. 집합제곱 그거를 원래 클래식 컴퓨터라면 0을 한 번 넣고 1을 한 번 넣어가지고 그 각 경우마다 결과를 다 도출해야 되기 때문에 저기서
그게 네네
나오고
네네
근데 그때 Y가 들어가줘야 그걸 제대로 읽을 수 있는 거예요. 그냥 0만 다 넣어가지고 중첩시키고
네.
그 게이트 거친 다음에
예.
다시 읽으려고 하면
네네네.
그 우리가 생각하는 그런 계산대로 안 나와요. Y가 되게 필요.
자, 근데 이게 중요한 건데 사실 이게 되게 중요해요. 근데 사실 이게 헷갈릴 수 있거든요. 그래서 당연하다고 느끼시면은 좋은 건데 그 아닌 경우에는 이게 되게 중요한 문제예요. 그러니까 그냥 F를 여기다가 바로 인풋에다가 바로 적용을 해서 그러니까 그 F가 뭐든 간에 이 스테이트를 바꾸고 싶다 뭐 하면은 문제가 뭐냐면은 내가 읽었을 때 확률적으로 나온다고 했잖아요. 그러면 그게 나온 게 어떤 스테이트에 의한 것인지 알 수가 없죠. 자, 예를 들어서 내가 잠깐만. 그러니까 요런 게 있다고 해봐요. x가 UF가 인풋 아웃풋 레지스터가 따로 구분이 안 되고 이렇게 바뀌는 거. 뭐 이런 걸 상상하시는 거잖아요. 그러면은 이제 2큐빗이라고 가정을 하고 뭐 1큐빗도 상관없어요. 예, 해봅시다. UF를 거쳐가지고 이거 거치면 F0가 나올 거 아니에요? 자, 근데 내가 F0랑 F1이 뭔지를 알고 싶으면은 이거 2번 하면 되죠. 근데 이거는 그냥 클래시컬한 거랑 똑같은 상황인 거고, 얘보다는 내가 좀 더 중첩의 원리를 사용해서 하고 싶다. 그래서 하다마드를 거쳤어요. 자, 그럼 이제 이 상태에서 뭐가 되는지 한번 생각을 해보자고요. 여기서는 지금 플러스 상태가 됐죠? 여기서는 지금 F0랑 F1이랑 중첩된 상태가 나올 거란 말이에요. 자, 이 상태에서 내가 매저를 했어요. 자, 매저를 해서 이제 뭐 어떤 값이 C가 나왔단 말이에요. 근데 이 C가 0 아니면 1이란 말이에요, 무조건. 인풋은 이제 두 개가 0과 1이 똑같은 확률로 들어갔지만은 이제 예를 들어서 F0, F1이 둘 다 0일 수도 있고 아니면 F0가 0, F1이 0, F1이 1일 수 있잖아요. 그러니까 이 경우에는 무조건 0이 나오겠죠. 그렇죠? 뭐 00이니까. 근데 얘는 01이니까 이 경우에는 01이니까 0 아니면은 1이 나올 텐데 내가 0이 나왔다고 해서 여기에서 0이 나온 건지 이 상황에서 0이 나온 건지 알 수도 없잖아요. 근데 이거를 반복을 한다고 해서 뭐 몇 번 충분히 반복을 하면은 이제 이 경우에서는 뭐 계속 0이 나오겠지만은 이 경우에서는 이제 운이 정말 나쁘면 좋은지 나쁜지 계속 0이 계속 나올 수도 있다고요. 확률적으로 이제 0과 1이 나오니까. 그러니까 이런 방법으로는 사실 굳이 이렇게 슈퍼포즈 하는 거에 메리트가 없다고요. 모든 걸 그냥 확률에 맡기는 거잖아요. 그래서 우리가 확실하게 알 수 있는 결과를 이 메저먼트 결과로 확실하게 알 수 있는 이제 알고리즘을 만드는 거죠. 어떤 상황에서 이제 확률에 의존하지 않고 확실한 결과가 보장이 되는 서킷을 만드는 거죠.
그들을 많이 해결해 주는 거고 그 과정을
네, 네, 네.
그러니까
네. 지금 이해하면 돼요. 지금 이해하면은 되니까. 네, 한번 let me move forward and then see how it works out for you. So I'm going to explain another algorithm. There are two more. So actually, I just said that we want the quantum algorithm that doesn't depend on the probabilistic outcome of the measurement, but will actually use the probabilistic nature of the measurement when we move forward. But here, Bernstein-Bazarani problem is still deterministic algorithm. So this is the situation where you have a function that takes n-bit string of bits and then gives you 0 or 1. And the formula of the function depend on n-bit string, the constant n-bit string a. So if you have a and your input is x, the output is given by the bit Boolean algebra sum between these numbers, these n numbers. So you take the multiplication bitwise, and then you add them up as an XOR or bit Boolean algebra sum. Now, the question is, I want to figure out what A is. So now the question is, I really want to figure out fully what this function is. So I want to know what A is. Then I get what the function is. How do you figure out what a is? In the classical algorithm, there is no other way than just query these n strings, n number of n strings. So first you take the string 00001 and then you put it into input. Then what you get is A0. So that's going to be the first bit of your string A. And you do this for all the other bits. However, when you use the quantum algorithm called Bernstein-Bazarani algorithm, you don't need n queries, you only need one. You can find out what A is by single query. So here's the situation. It's almost similar. It's the same. Basically, the formula is the same, but only difference is that you have a Hadamard gate on output register at the end. Now, it doesn't really matter, but well, just put it anyway. So we're going to talk about, we're going to compute each step. So 1, 2, 3. So I omit the 0 state. So first step, at the first stage, the quantum state becomes this. So you already seen this. So output register is minus, input register is a superposed state of every single base state. And then you apply the quantum state, quantum oracle. What you get is it 2? Yes. Is this. So might be weird at the first glance, but let's see why we get this. Yes. So let me put it here. So as I said, you have x and let's see, and you have minus state as an output. So here I'm assuming my x in this notation is simply a base state. Okay, so this is one base state. Okay, and I want to put that in the quantum oracle. The base state does not change. What happens here is now something weird, so I would say. So let's take UF on xn tensor minus 1. So this is same as if I expand this, this is xn tensor 0 minus xn tensor 1. So let's forget about coefficient now. And this becomes xn tensor f of x minus fn tensor 1 plus f of x. Okay, so as I said, f of x is either 0 or 1. So if you combine this together, it's xn f of x minus 1 plus f of x. But this is either 0, 1 or 1, 0, right? So it only matters what sign does this have in here. So this sign is this, xn minus. So if fx was 0, it's 0 ket minus 1. If fx equals to 0. And if fx equals to 1, then it's 1 ket minus 0 ket, right? So if I take this as my base state, then when f of x is 0, I need to have a plus sign here. And if I get this one, then I need to have a minus sign applied to multiply to the base state when f of x equals to 1. So that's the expression that I need. So exactly the same result. No matter what value of f of x is, this is my formula. So that's right here. Okay. And then let's think about when we take the Hadamard gate. So let's think about a little carefully here. So let's take it in a different perspective. Think about what happened. What's the formula when I take the Hadamard gate on the base state? So x is either 0 and 1 or 1, and based on whether it's 0 or 1, it has this formula, right? When x is 0, it's 0 ket plus 1 ket, right? But when x is minus 1, if x is 1, then you get 0 ket minus 1 ket. So it only differs by this coefficient, actually the phase. So we can determine this coefficient or sign in terms of x by taking formula minus 1 to the power of x. So that's your formula for the Hadamard on x, regardless of what x is. But now let's take a further more. So I want to set the variable for this ket as y. So y range from 0 to 1. Okay, so 0 and 1. And then what goes as this coefficient is if y equals to 0, I always want to have a positive sign, right? So if I multiply y to x and put that as an exponent of minus 1, I always get plus 1 when y equals to 0. And when I have y equals to 1, I want to have this symbol, this sign. So then I get the same result by having the same formula, y times x as exponent. So you can rewrite your Hadamard on x ket as this formula. Okay. So now let's put that in the n-qubit state. So n-qubit state is, let me write it here, applying Hadamard on every qubit hx0 here. And if you write down in this way, so there are n number of 1 over square root of 2. So we have a coefficient here, and we have, I'm going to label it with the same label of same index of x. So y n minus 1 from 0 to 1, minus 1, y n minus 1, x n minus 1, y n minus 1. That's for the first part, this part. And then you do this for the others. Okay? So and then I'm going to take the distribution rule over the tensor product. Okay? So far that makes sense, right? Does it make sense? It's only a formula. Okay? So this is it. Okay? So this is what it means. So instead of writing the tensor product in a long form, I put the big tensor product here, indicate that it runs, the index runs from 0 to n minus 1. So I is the index here for x and y. Okay? So again, xi is the ith digit of the value x, which is the base state of the input register. Okay? Y is just the indication of the all possible the base state. Okay. Now let's wait. So this is, what is it? So we apply the Hadamard gate, and then let's take the quantum oracle. Okay. So we are taking quantum oracle on here after we put all the Hadamard gates. Oh, by the way, so no. So that's after second stage, and then yeah. So here we have. So here we have still before the quantum oracle. Is it? No, after quantum oracle. Let me check. So here we have Hadamard. Just we apply the Hadamard here to get this minus 1 tensor, what was it? xi, yi, yi, right? And then we want to tensor product that with the input output register. So it's minus 1. So this whole thing is input, and this is the output. Now we want to apply the oracle on here. So this is my psi 1. Let's try to get the psi 2 after we applied Hadamard. But now I can rewrite this a little bit in a different way. So what I have here, think about the distribution rule of the tensor product. I just take the collection of y0 to yn minus 1 and then take the tensor product of those n 1-qubit state, right? So if I take all the y0s to yn minus 1, I can rewrite that as a number in between 0 and 2 to the n minus 1. So that number range from 0 to 2 to the n minus 1. So I can rewrite this as y range from 0 to 2 to the n minus 1. And then for every time I take this tensor product, I need to take consideration of this coefficient. So these coefficients are all added, multiplied together. But this is an exponential function, so you can rewrite this as the same thing as minus 1 to the sum of these exponents. So this is minus 1 x 0 y0 up to xn minus 1 yn minus 1, and then you multiply it to n-qubit state. So that's the input register here. So input state here. Okay. So that's what I just wrote here. This is the input. So psi 2 is y from 0 to 2 to the n minus 1 minus 1 x times y times minus. Okay, so forget about the don't worry about the coefficient here. So 1 over 2 to the power n minus 2. So just the psi 2, and then now let's try to apply the quantum oracle. So what does it say? The same thing applies here. So it's minus 1. It's basically 0 minus 1. So when I apply f, I am looking at y as my input. Don't be confused. Y is just the variable, name of the variable. Now, this y represents the base state of input register. So this is what goes into the function. And then you compute the value of function f of y. Yeah, but I think it might be confusing in the next sentence. But so anyway, this is what goes into the function, and then you compute that value, and then it is affected on this output register. But remember what happened in the previous algorithm. Because of this minus ket state, this only changes the sign of minus ket state. If f of x equals, or in this case, f of y equals to 0, it remains the same as ket minus. But f of y equals to 1, it changes the sign. Okay, so when you apply the oracle here, the third stage becomes for each input y, you get the same. The only difference is that you have minus 1 f of y multiplied, and then 0 minus remains the same. So, right, why do I have another, y, so y range from 0 to 1, and it right? So x. Oh, sorry. Okay. So I'm sorry for. So this is the Hadamard gate on this base state. Okay. So yeah, I forgot one more step here. So if I apply Hadamard on all the superposed state, like this one, then I get the sum of these over x. So I already have the double summation, y from 0 to 2 to the n minus 1, minus 1 to the power x times y, y. Okay, that's my first superposed state. And you can switch the role of x and y here because they are symmetric. So that's what I did in the slide. So you can simply switch the role of x and y to say this is the sum of x. Okay, so and then if I take x here, this becomes f of x, and I need to put x sum over x here and sum over x here also, and that's after you applied the oracle psi 3. Okay, that's right here. That's right here. So I'm going to finish the computation and finish explaining it, and then I'll give you time to ask or discuss. So now let's try to group them together. So first, I'm going to switch x and y. So y goes first. Doesn't matter because as long as I don't delete the terms, so I can group all the ket y state and take all the coefficient of ket y state as the sum over x. And oh, sorry, I think I forgot to say, so this is minus ket, sorry, not 1. And then let's think about the original definition of function f. So this is, as I said, given as a times x. So how does a times x defined? It's a n minus 1, xn minus 1, plus up to a0, x0. So I'm going to plug that in here. So I can, so I think I need to explain more steps here so it doesn't go directly from here to here. So what it says, what I'm trying to say is I want to rewrite this part as this part, but there's more. There should be more explanation. So let me write it here. So I need to write x to the 0 to 2 to the n minus 1, f of x plus x times y in different form. So let me write it this way. So it's 2 to the n minus 1, a n minus, so one more step, a times x plus x times y. So then I can combine a plus y times x. So it's a Boolean algebra, but it's about the same multiplication and addition as the real number. So I can do this. And then now let's think about in a little bit different way. So I can split my x as xn minus 1 up to x0 in a bit string. Okay, so what I'm actually doing here is distributing all the xi's, so over the index I from 0 to n minus 1, I'm taking xi from 0 to 1 and taking ai, yi multiplied to xi. Okay, so same thing as we did before. So you can distribute to get the simpler form of the same equation, but now we are going backward. We're going to make the simple form of the formula into a longer form by using the distribution law. So then you get this one. Now we get this one. So we're going to think about the result. So this is after you apply the oracle. This is after you apply the oracle. And if y is not a, let's think about what would happen. So there is some index I such that ai is not equals to yi if a is not y for some I. Okay? So then, if they are different, what would happen? If you add two different numbers in Boolean algebra, it's always 1, right? If they are the same, they are added together to get 0. But if they're not different, then it's always 1. So you get a survive of xi. So xi actually survive. So what happens when you have survival of xi? So xi runs from 0 to 1, right? And it's an exponent of -1. So when xi is 0, it's +1. And when it's 1, it's -1. So +1 plus -1 becomes 0. So this summation becomes 0 when ai is not equals to yi, when ia is not equals to y. Okay? When this summation becomes 0, then this whole multiplication becomes 0. Because if one of these multiplication factor becomes 0, then everything is 0. So what does that mean? If you have y not equals to a, then this whole thing becomes 0, this whole thing. Because that's the same thing here. Okay? So if you have a 0 coefficient, that means you don't have that state. It just vanishes. So even though the formula seems like you have all the state from 0 to 2 to the n minus 1, it turns out that except for the state A, everything vanishes. You only have A. Okay? You only have A. So that's what it says. You only have A. Okay? When you take the measurement, I think that was after the Hadamard. No, it's not after Hadamard. It's after what? So we don't need this. Sorry. So there's the typo here. So we don't need this. You just take the measurement. Okay. So after you take the oracle, take the measurement, there's no other chance than observing A. Okay, so you always get the observation of A. So you take the measurement on each input string. So the result, the measurement outcome on each input register is the actual bit in A. That's your A. Okay, because this is the output register, the state after the result state after you apply the quantum oracle. So situation is simple if you just look at the process. You set the circuit, a circuit like this. There's a typo considering that it's a typo, that there's no steps to apply here. Just take the measurement right away after you take the quantum oracle. You read off the bits. That's your A. You fully determine what function is. Okay. So I think it's not enough time to give you some discussion, but I'll take any questions if you have. So in here, you can say it's an application of, so in some sense, it's a little bit more generalized generalization of the Bernstein-Basrani. I'm sorry, the Dutch-Jozsa algorithm. So you have a question? No? Any questions? Haju, do you have questions? No? Yes.
만약에 그 x가 이제 총한 5개의 텐서로 이제 주어지고 a가 만약에 막 100 이렇게 되면
No, you need the same number of input or the number of bit string of A.
x의 무슨 이렇게 주어질 수 있잖아요.
X 100에 X의 5승. What do you mean by that? So you want n to be 5? What's n here?
x0의 코에피션트가 100일 경우에는
A0 is 100? No, A0 is either 0 or 1.
개수가 0 아니면 1일 경우에만
Yes, so A is also a bit string. So you can only take the Boolean algebra on 0 or 1. Any other question? Yes.
제가 어디까지 하다마를 n개 텐서 프로덕트 하는 그 포뮬러까지 이해가 됐는데
This one? Okay.
다음 시간에
Mhm.
사이즈가 딱 나오는
Mhm.
첫 번째 포뮬러의 의미를 어떻게 도출했는지 모르겠습니다.
Okay, so I think that's going to be our last part of our class. So let me do this for you. The site 2 was given by y from 0 to 2 to the n minus 1. Sorry, I forgot the x. So here it's x times y, x times minus. So this whole thing is input, and this is output. Now, let's take the unit, the quantum oracle to get psi 3, x and y, and we're taking UF to each of these states, right? So then we get the same. Now, this one is 0 minus 1, right? So when you do this, it's x tensor f of x and x tensor 1 plus f of x, right? So no matter what f of x is, if you combine together, it's 0 minus 1 or 1 minus 0. Only differ by minus sign. Okay? So it's plus 1 when f of x is equals to 0, or minus 1 if f of x equals to 1. So I can rewrite this in terms of 0 minus 1 times minus 1 times x. Okay? So now let's put it back. So we have x to n, y to n, and minus 1 f of x, minus 1 xy, x tensor minus. So all I need is just put these two together. So plus, this plus is plus O plus. It's always a Boolean algebra plus, but that really doesn't matter in this case because it's always in the exponent of minus 1. So no matter how big number is, you can always take the parity of the number. So that's the size 3. I put it in the slide. Okay, so if you have any other more questions, let me know, or we'll see you on next Wednesday.